Good afternoon, everyone, and welcome to our webcast series, 2021 NFPA 79 Updates. In these webcasts, experts from both UL and Eaton's Bussmann series team take a closer look at the newest edition of NFPA 79, which was published earlier this week. My name is Shannon Stokes with the Bussmann series team, and I'll be your moderator for today's webcast. I just released 3 poll questions to each of you. Your input on those is greatly appreciated. Today's webcast focuses on SCCR for machinery. Our speakers are Joe Pavia with UL and Joe Pavia with Bussmann. Throughout the webcast, you are welcome to submit questions for our speakers. We'll try to dedicate the last 15 minutes of this webcast to addressing as many of those questions as we can. Once we've ended this webcast, you will be able to view it on demand within the same portal you used to join us live. I'd like to introduce Joe Pavia, who has nearly 30 years with Bussmann Series Solutions, currently serving as Field Application Engineer. Joe specializes in training on the design and application of overcurrent protective devices and equipment in electrical distribution systems, serves on a UL panel, and is active in IEEE, IAEI, and NFPA activities. I'd also like to introduce Joe Pavia, Primary Designated Engineer at UL for Industrial Control Equipment, Components, and Assemblies, including control panels and industrial machinery. His 45-year tenure with UL has covered countless codes and standards and technical committees. He sits on NEC and NFPA committees and serves as technical advisor for the IEC. This webcast includes 3 parts. Part 1 highlights SCCR and its benefits for industrial machinery. Part 2 covers how to meet industrial machinery codes and standards for SCCR requirements. And Part 3 discusses SCCR and available fault current with multi-panel machines and arc flash. I will now turn the floor over to John. John?
Thank you, Shannon, for that kind introduction. And good day, ladies and gentlemen. Once again, it's a pleasure for me to work with my esteemed colleague from Bussmann, Mr. Joe Pavia. We have a wealth of excellent information to share with you today, and so without further delay, let's begin. Let's start with a discussion on focusing on the term short circuit current rating. What we see here on this slide is what I would call a layman's definition of the term short circuit current rating. There is an official definition, and it's found in both the National Electrical Code and NFPA 79. However, what I like to do when I provide training on the concept of short circuit current and how it relates to control panels and machinery, I like to show what I would call a layman's definition, and that's what you see on the screen here. We'll get to the actual definition or the official one in a few moments, but I think it's easier to see when you read the words what a short circuit current is and how to capture it in your mind. It is the amount of fault current an industrial control panel or industrial machinery can safely withstand during the event of a short circuit. So what you see in this particular slide is an industrial control panel. It has a label. That label would be the main nameplate, which is generally provided either on the outside of the enclosure door. If it's on the inside, it's on the enclosure door as well, so that it is clearly visible. As part of the nameplate, you would find the short circuit current rating. And you can see in this example here, the short circuit current rating is 50,000 amps. If a fault occurs, and in the diagram, see the fault occurring in the conductors going out to the motor. For UL purposes, we generally consider a fault occurring either in the conductors going out to the load or in the load itself. And in this case, we have a motor, which is a dynamic device, and it's often susceptible to breakdown. So if we had a 35,000 amp fault in the conductors or in the motor being controlled by this panel, would the panel be safe under a short circuit condition? Would it be able to withstand the 35,000 amps without damage that would cause a hazard either to personnel or property? And the answer is yes, because as I mentioned, the label on the panel clearly indicates that the short circuit current rating is 50,000 amps and the fault is less than that at 35,000 amps. So let's continue on with some important definitions that I believe will help you further understand the concept of short circuit current rating and available fault current. So here we have an excerpt from NFPA 79, specifically paragraph 7.2.9, and this is also found in the National Electrical Code in Article 110, specifically section 110.9. A short circuit current rating or interrupting rating shall be at least equal to the available fault current at the point of application. Now, when we talk about short circuit current rating, it is truly an interrupting rating for active devices. And when I use the term active device, I'm talking about a circuit breaker or a fuse, because it actually can interrupt a short circuit current. So the short circuit current rating on a fuse or circuit breaker is also an interrupting rating. I recall seeing on a fuse the acronym AIC, amps interrupting current. That tells you that that particular fuse can actually interrupt current at the rating that's marked on the fuse, whether it's 100,000 amps or just 10,000 amps. It is not only a short circuit current rating, it also has an interrupting rating. You can see in 729, we go on to read where the short circuit current to an overcurrent protective device includes additional currents, say, for example, other than from the supply. So, for example, from motors where you have a collapsing magnetic field, or maybe from power factor correction capacitors where you have the energy stored in the capacitors. Under a short circuit currents, you could have those particular factors can be considered as well. So further on with definitions, we've got some changes that are occurring in NFPA 79, and they're basically taking the lead, or taking the lead from what's happened in the National Electrical Code with regards to fault current. We're now not using the term short circuit current, but we're using the term fault current and fault current available, or available fault current. You see some sections of NFPA 79 that are going to be new for the 2021 edition. And again, these basically come right out of the NEC. Fault current is now the current delivered at a point on the system during a short circuit condition, whereas fault current available, or available fault current, is the largest amount of current capable of being delivered at a point on the system during a short circuit condition. There is a subtle difference between the two. Fault current is basically the current that flows under a short circuit condition. So you can see we talk about a specific point on the system. So depending on where you're at in a particular circuit, the fault current could vary considerably. For example, if you are downstream from the source of supply, you have considerable impedance between the source of supply and that point where you're at, and so the fault current can be reduced considerably, whereas the available fault current would be the current that's at the point where the supply is connected to the equipment, and that's generally the point at which you're most concerned, because there you can determine if the equipment has an adequate short circuit current rating. And then we see we added some annex material indicating that short circuit can occur during abnormal conditions, such as a fault between circuit conductors or a ground fault. So moving on with some more definitions, NFPA 79 and again the NEC are in lockstep on what is a short circuit current rating. This is the definition that I said is the official one, and if you look at it, the way I read it, it's very technical. Yes, it does define from a technical perspective what a short circuit current rating it is, and basically how it's established. When we talk about sustaining damage, the determination whether unacceptable damage has occurred can only be determined by doing short circuit testing. And then, of course, when we talk about acceptance criteria, basically we're referring to the requirements that are in a product standard that defines what is acceptable damage under short circuit conditions for that particular product. There are many, many products that have short circuit current ratings, and of course the acceptable damage or the level of acceptable damage can obviously vary considerably depending on the type of product. Obviously, when you're doing short circuit testing with fuses or breakers, virtually no damage can occur because obviously those active devices are there to protect equipment downstream, and their job is to adequately interrupt the short circuit current. Moving on further, more information from NFPA 79 and also NEC Article 100. We're going to talk about industrial control panels and machinery in this particular webinar. So we want to make sure that we understand the purpose of talking about a panel and its relationship to machinery. The definition for a panel is assembly of two or more components consisting of one of the following. And we have power circuit components, we have control circuit components. I think all of you are familiar with the different kinds of components you see in items 1 and 2. And then, of course, you could have a combination of both. And then the industrial control panel does not include the controlled equipment. So basically, when we talk about controlled equipment, we talk about the loads that are connected to the industrial control panel. And now we have a definition for industrial machinery. Industrial machinery is a power-driven machine or group of machines working together in a coordinated manner. Not going to read through all of that, but for those of you that are interested in how to define an industrial machine or machinery, you can find the definition in NFPA 79. Also in the NEC Article 670, which covers industrial machinery, or specifically the installation of an industrial machine, you will find this same definition. And it applies to not only one individual machine, but it also applies to a group of machines. Industrial machinery can consist of multiple machines working together to provide a specific process, for example, in a manufacturing environment. Another requirement that's very important is you see in paragraph 4.3 in NFPA 79, which deals installation and use of listed or labeled equipment. This is also covered in Article 110 of the NEC. Listed and labeled equipment shall be installed and used in accordance with any instructions, including in the listing or labeling. And that's very important because you'll see a lot of requirements in 79 and more importantly in the NEC where a listed piece of equipment or a listed product is necessary or must be provided in order to comply with a requirement. But beyond just using a listed product to determine code compliance, you must also make certain that any installation instructions, any kind of warning information, any information that's provided with that product, that's part of the listing and labeling. Because I can tell you as a member of UL staff, when we evaluate products, we certainly not only evaluate the product itself, but we evaluate the material supplied with it, the printed material. And it comes in many different forms. It could be just simply labels. It could be an instruction manual. It could be paper that's considered a stuffer sheet put into the packing container that the product is shipped in. All that material is really part of the listing. So it's very important to make certain that it's read and understood, and if there's any instructions that need to be followed in order to ensure proper installation of the product, those instructions must be followed in order to ensure a code-compliant installation. Now here in this particular slide, we're showing a couple of 9 and NEC Article 670, where we've got a little bit of a comparison here. First, we're going to talk about the nameplate required for industrial machinery. And the nameplate requirements in in NFPA 79 are covered in Chapter 16, specifically paragraph 16.4.1. We have similarly nameplate requirements for machinery in Article 670, 670.3 paren A paren 4, that's the section. They're quite similar, except you will see that the NEC only deals with the electrical parameters. It does not get into specifics like the manufacturer's name or trademark or serial number or that kind of information. That's typically covered in a product standard, like, for example, the standard that UL uses for industrial control panels, 508A. So if you take out that information, basically the two documents are covering nameplate information quite similarly. There is a little bit of difference, and that is the location of the nameplate. In NFPA 79, the nameplate shall be provided on the outside of the industrial control panel or the machinery, whereas NFPA 670 is silent on that, and it uses the term plainly visible. I can tell you that plainly visible is not defined in either the NEC or NFPA 79. It's been a term that's been discussed certainly at length by the NFPA 79 committee, trying to define what that means so that it's clear to enforcers and certainly users of the document what the requirement is, how to interpret it. And we had quite difficulty coming to a conclusion on what that meant, so we just left it the way it was. We tried to substitute a term like clearly. That didn't work. So I think more work is necessary to provide clear guidance on where the nameplate shall be located, and I expect that to take place in the NEC in this upcoming cycle. We also have a requirement for the available fault current to be marked on the machine nameplate, and that's in NFPA 79, Chapter 4. We also have that in NEC 670.5 paren 1. And then the NEC has a requirement that's not in NFPA 79, because, of course, NFPA 79 basically deals with just the construction of the machinery, whereas the NEC deals with the application of the machine in the field. And there is a requirement that machinery needs to be field marked with the maximum available short-circuit current. And, of course, that can only be determined in the field. That requirement also includes a need for marking the date at which the calculation is made to determine what the available short-circuit current is. That date is important because changes could occur in the electrical infrastructure of the machinery, could occur in the facility itself, either inside the facility or outside the facility where, for example, the utility might make some changes to the equipment that they're using to supply a building. And of course, that could easily affect the available short circuit current. So that's why the date certainly is important. Okay, we're going to move on, and I'm going to turn the program over to my colleague, Joe, and he's going to get into determining the individual panel machine short circuit current ratings. Joe, it's all yours.
Thanks, John. It's always great listening to you reading up the definitions and so on. All right, so let's get into determining the individual panel or machine SCCR. How are we going to determine the SCCR? So let's start with what can we do to determine the SCCR? Well, number one, we could basically take it to a testing laboratory and have our machine tested and have it blow up to find out exactly what the SCCR would be. And then you would have to go ahead and rebuild the machine. And most likely we wouldn't do that. The second option that we would have would be to use the UL 508 or a analysis method that basically UL 508 SB can do for you. Or you can basically do an approved method, engineering method that would do the same thing and determine the SCCR for that machine or the industrial control panel itself. All right, so let's look at a machine or an industrial control panel. And in general, every machine or industrial control panel looks alike to me. All right, you guys make it do different things, but to me, you basically have power coming in. So you either have a main disconnect or main terminals coming into the panel or machine. Then you basically have power distribution, all right, feeding all of the branch circuits. So you basically have a main coming in and the power distribution throughout the panel itself, and then you have your branch circuits. And so we want to determine our SCCR based on all the components that we have in the on the machine itself, as well as in the industrial control panel. Now, there are some exceptions, all right? So basically, we are going to be looking at all of the branch circuits and feeder circuits on the power side of things. We don't want to look at the control side of things. And you're basically looking at, well, what is the control side? Well, I'm not going to get into the details of that yet because we don't have that much time in this 1 hour presentation, but we're going to just basically look at all power circuits in general. Now, there is an exception that basically says no matter what the load is, on the secondary side, circuits operating at 24 volts max and supplied from a source that basically has an output of 100 VA. So basically a power supply that's 24 volt output and no more than 100 VA, that no matter what is feeding it, it's always considered a control circuit and is not considered in the SCCR determination. Right? All right, so let's look at how do we determine the SCCR. So I tried to break it down. We're going to take a look at the UL 5088. UL 5088 SB gives us the guide in calculating short circuit current ratings and taking a look at all the components that we need to do to determine that SCCR. So here's what I broke it down to. There's 3 steps. Step number 1, and as you can see, we have fuses and breakers. So you've got to take a look at the overcurrent protective devices in the panel, right, on the power circuit. Right? We look at all of the overcurrent protective device and we look at the smallest or the lowest interrupting rating of that device. And that is going to be step 1's answer. So for instance, if we have all fuses in the industrial control panel or machine, most fuses that we have in there are going to be 200,000 amps. So the machine, the lowest rating is going to be 200,000. In the breaker scenario where we have, well, we can have 100,000 amp breakers, we can have 10 KA breakers. But in general, whatever the lowest interrupting rating is of that overcurrent protective device, so if we have a 10 KA breaker protecting that control transformer or that power transformer, then the whole panel or machine brings it down to 10 KA. So the first step is we want to look at all of our overcurrent protective devices and find the lowest interrupting rating of those devices, and that's what step number 1 is. Now, the panel will not be any higher than that. The SCCR cannot be any higher than the lowest overcurrent protective device interrupting rating, right? Then we move into step 2, right? And step 2 is looking at the components. So as at the right of the slide, you're going to see the power distribution block and the contactor. Well, in general, a contactor is rated for 5 KA. And in general, a power distribution block is rated 10 KA. Well, we need panels and machines to be higher rated than that. And so step 2 is looking at the component SCCR along with the associated overcurrent protective device. So for instance, if we have a contactor with a breaker, let's say, the combination rating could be, let's say, 35,000 amps. So now that brings that contactor rating from 5,000 amps up to 35,000 amps. And that's a combination rating, just like we would have with a power distribution block if it's protected with a fuse or a circuit breaker. So we want to make sure step number 2 is taking the components and along with the associated overcurrent protective device to boost that rating up from the default rating itself. And then finally, step number 3 is taking a feeder, a current limiting feeder device to increase the branch component device. So for instance, if we didn't have a combination rating with this contactor itself, and the contactor is at the very bottom, like I'm showing, that contactor is rated for 5,000 amps. But I can increase that 5,000 amps with a feeder device, a current limiting feeder device, as long as the I peak of that current limiting device is less than, in this case, 5,000 amps. And so I'm going to break this down a little bit for you. This way we can understand the different steps that we have. so let's just look at step number one. And as you can see, the upper left-hand corner, I'm putting the steps that I'm at that time. Step number one is pretty simple, right? So we're going to look at all of our fuses and all of our breakers in this panel, and whatever the lowest interrupting rating is, our panel can't be higher than that, and that will be our answer for step number one. So if the breakers are rated for 65,000 amps and the fuses are rated for 200,000 amps, step number one would be a 65,000 amp panel at this time for step number one. If for some reason I use a 10 kA breaker in front of this transformer, then the whole panel moves down to 10 kA. So we have to look at what, besides the overcurrent protective devices in the panel, what is our SCCR goal? Are we shooting for 10 kA? Are we shooting for 65 kA? Or are we shooting for 100 kA? So what is our goal? And then we have to make sure that all of our overcurrent protective device interrupting ratings equal that goal or is greater than that goal. All right, that's step number one. Pretty simple. Now let's look at step number two. Step number two, determine the SCCR rating of each component with its associated overcurrent protective device. And as you can see to the right, the panel, the power distribution block has a rating by itself. But if we have a fuse or a circuit breaker ahead of it, that's its associated overcurrent protective device. And so what is the true rating of that power distribution block? Is it 10,000 amps, or is it 65,000 amps or 100,000 amps? And that's what we have to do. Make sure that we take that component and tie it to the associated overcurrent protective device to get that combination rating that we're looking at. And then on the panel itself, we'll also have 3 squares down at the bottom and 1 big square. So one's a drive on the right, and the other 2 are basically contactors, and they're protected by their associated overcurrent protective device. So in general, contactors and drives, 50 horsepower and less, have a standard SCCR rating of 5 kA. But with the associated fuse or associated breaker, it can jump up to 65,000 or 100,000 amps. And so we want to make sure step number 2 is looking at the combination ratings, and that will be our answer for step number 2. And basically we cannot exceed step number 1 because that's our overcurrent protective device and we can't change that. Right? Now let's look at step number 3. Step number 3 gets a little bit difficult, and I'm not getting into the details of how to basically determine it, but we want to give you guys an idea of what is the SCCR, how do you do a quick determination of it, and then we can expand on that down the road. But in general, step number 3 is my main or my feeder device, we look at the feeder device, is the feeder device current limiting? And so in this case here, we put an example where we're using a current limiting fuse on the main. The main, in this case, is considered a feeder device. Basically, it feeds a power distribution block, which is in the feeder circuit. Okay, so I can't change that device, all right? But I can change the branch component, not the branch overcurrent protective devices, only the branch components. So the main fuse, in this case, the current limiting fuse, the main, can change the branch contact, the 2 contactors, and the drive. Right? It will not be able to change the transformer fuses at all as well. And it can't change any overcurrent protective device, just branch component. And with that, then that will help me boost up my overall SCCR for the machine or for the panel itself. All right, so in summary, we want to basically do a quick summary of what we basically covered. So step number 1 is determine the minimum interrupting rating of all of our overcurrent protective devices themselves. So all the breakers and fuses that are in our panel on a power circuit, we want to look at their interrupting rating. And that's going to be what step number 1 is. And so if it's a 50,000 amp breaker that we have in there, the panel can't be higher than 50,000 amps, but it could be lower based on step number 2 and step number 3, but it won't be higher than that. And then we move into step number 2 again. Step number 2 is looking at all the components, the feeder components, as well as the branch components with the associated overcurrent protective device, which is the combination rating for those different components. And what is the lowest one I have? So if the step number 1 is 65,000 and step number 2 is 10,000, then right now my panel is rated for 10,000 amps, or SCCR. Now let's move into step 3, because step 3 can sometimes boost up step number 2. And step number 3 is using, again, a current limiting feeder overcurrent protective device to boost up the branch components themselves and their SCCR rating. And so it's possible that a step number 2 was based on a branch component that was only rated for 10 KA, and then step number 3 could, with a current limiting feeder device, can boost up that component that was 10,000, and it could push it up to 65,000 or 100,000. We just have to look at the charts and stuff like that. And then finally, whatever the lowest SCCR that we find in the steps, basically number 4 is basically that's where our SCCR is for our panel. All right, so I deal a lot with industrial facilities where they have machines that are over-duty, if you want to say. So in this case here, this machine is rated for 10 KA. And the variable fault current, the available fault current, is almost 35,000 amps, just under 35,000 amps. And so what can you do? And that's where we have to take into consideration what can we do to boost up this SCCR, because right now we're in violation of the code, we're in violation of UL 508A, and we're in violation of NFPA 79, but mainly because we're the code and because of arc flash. And we're going to talk about arc flash down the road a little bit. All right, so what can we do? Well, we can install a transformer in front of it, hopefully drop the fault current to below 10,000 amps, and then we cover the SCCR of this machine. So we can do that if we wanted to. That's expensive. Or we can add conductors. So basically, we disconnect the conductor out of this machine, run it around the building a couple times, and then bring it back into the machine. And because of the resistance in the conductors, basically we've dropped the fault current to below 10,000 amps to cover this machine. That is not necessarily feasible, but it's one of our options that we could possibly do. And then the other thing we can do is change components. All right, so, but if we change components, sometimes we'll have to need, if it's a UL listed panel or a third party listed panel, we would have to get a field evaluation once we change the components. So if we change the components and boost up the SCCR of the components and equal the 35,000 amps that's available, then we may have to get a field evaluation and we modify the equipment itself. And then finally, what we could possibly look at is installing current limiting fuses, which is in the feeder device, to see if we can boost up any of the components and use the let-through, the peak let-through of the fuses, to see if it will boost up our component SCCR and readjust the SCCR of the machine itself to greater than, let's say, 35,000 amps that I'm showing. And so there's 4 ways that I see that we can change this machine that's possibly already installed or being installed, and they didn't realize that the available fault current was as high as higher than the SCCR. So you can add a transformer, a high impedance transformer, to reduce the fault current. You can run longer lengths of conductors to reduce the fault current. So the first 2 options are reducing the fault current. And then the next 2 options is increasing the SCCR of the machine and of the industrial control panel itself. And now I would like to turn the presentation over to John, and John will basically talk about labeling as as well as determining SCCR for the overall machine itself. John, take it away.
Thank you very much, Joe. Well, now that you've determined the short circuit current for a piece of machinery, how do you comply with the requirements for labeling? Well, I had previously identified the paragraphs in the sections in NFPA 79 and the NEC that cover the requirements for the labeling. So we've covered this already. I think it's pretty clear what kind of information needs to be provided on that nameplate. So let's take a look at a typical nameplate. And what we see here is a nameplate from a machine that has been identified by number to correspond with the numbers in paragraph 16.4 of NFPA 79. So you can see that a short circuit current rating, which is required as item number 6 in 16.4, is provided on this sample nameplate. We see number 6 identified on the nameplate, and it's 5 kV. 5 kV. I'm not sure why the A is there. That may be a little confusing, but actually, I'm sorry. The V is there, and I'm not sure why that's there. That could certainly be misleading. The rating is 5,000 amps, and so to have it marked as 5 kVA, that is not correct. But the intent here is to show that the nameplate does include the short circuit current rating. And while we're looking at this nameplate, I'd also like to point out that item number 5 in the list from 16.4, the nameplate does not satisfy that requirement. It's not showing the maximum ampere rating of the short circuit and ground fault protective device to be used to protect the machinery. So this is a typical nameplate, and this is where you would express the short circuit current rating. It would be provided with the other electrical parameters required in paragraph 16.4 of NFPA 79. And that would also, of course, match with Article 670 requirements for industrial machinery. So let's move on and talk about determining the overall machine short circuit current rating. Joe's given us a lot of good background, and so let's put it to use. Let's first talk about the easiest scenario in terms of determining the short circuit current rating. That's where you'd have a single supply to the machine, and the machine having a single industrial control panel. In that situation, it's very straightforward. Whatever the short circuit current rating is for that particular panel, then that would become the short circuit current rating for the machine. Very straightforward. That's essentially a no-brainer. Where it becomes more challenging is when you have multiple panels. For example, multiple panels on a machine where you could have a single supply or multiple supplies. And there you have to look at the circuitry and see how the panels are connected in terms of their relationship to one another in the circuit diagram. And we're going to talk about that. So we've got a couple of different scenarios here. We've got multiple panels and multiple supplies, and then we've got multiple panels in a single supply. So first, we want to make sure that we identify all the supplies from the facility. Many machines certainly could have more than one supply. You could have a supply for the power circuit, and then you could have a separate supply for the control circuit. Or you may have a machine that needs different voltages for different power circuits. So you could have multiple supplies for the power circuits and a separate source for the control circuit. So the machine could have different supplies. The requirement for displaying the short circuit current rating is such that you need to identify the rating for each supply. With the exception of one for control circuits, there is no requirement to identify the short circuit current rating for a supply for the control circuit. For the power circuits, multiple supplies, each supply would need to be identified with its short circuit current rating. So how do we deal with that? What are the situations that we could be faced with? Well, just a recap of what Joe covered, we can apply essentially the training that Joe just enumerated or elaborated on for determining the overall short circuit current rating of a panel. We can apply that to machinery. For example, you can determine the short circuit current rating for each control panel associated within the machine if you have multiple control panels. Then you look for the lowest short circuit current rating of all the panels that are provided with the machine, and then the industrial machinery short circuit current rating. The short circuit current rating for the entire machine becomes the industrial control panel with the lowest SCCR. This is basically the weakest link method. So as Joe described it for you, when you're working on an individual panel, use the same method when you're talking about determining the SCCR for machinery. So let's take a look at a couple of examples here that can be a bit challenging. Here we have multiple panels with a single supply. The first thing we have to determine is to look at the circuit diagram. Do we have a main panel that's feeding the other panels? In other words, are those other panels sub-panels, or are all the panels being fed from the same supply where they're all essentially electrically connected at the line terminals? So if we have a situation where we have sub-panels, those sub-panels may have a short circuit current rating less than the main panel, as we see in the example here. So if we don't do anything more than using the weakest link method, obviously the short circuit current rating for the machine then defaults to 5,000 amps. If we need a higher rating, if that 65 kA rating is important, what one could do is do a study on the machine itself to determine what the available fault current is at those sub-panels. It can be done. It's a bit of a challenge, but you have to consider the size of the conductors going from the main panel to those sub-panels and the length of those conductors. And there are programs out there that will allow you to determine what that available fault current is. If you're certainly going to know the available fault current at the line terminals of the main panel. If you can somehow determine what that available fault current is at the line terminals of those sub-panels, basically then you can determine if they're protected. In other words, if those 5 kA ratings are adequate. So for example, if you had 50,000 amps available at the line terminals of the main panel, and you went through a study to determine at the line terminals of those sub-panels that the available fault current was 5,000 amps or less, then those sub-panels essentially are protected. And so now the entire machine takes on a short circuit current rating of 65 kA because the sub-panels are protected, and the main panel, which has a rating of 65 kA, is greater than the available fault current of 50 kA at its line terminals. So you have to look at the circuit diagram and determine how those panels are connected, whether they're sub-panels or if all of the panels are independent of one another. And then, of course, we have multiple panels with multiple supplies, and we would apply the same concepts here. Again, we would need to determine from the electrical diagram if we have a main panel and sub-panels, or do we have all the panels connected to the same supply being independent of one another. And then we would need to determine how these panels are fed in terms of the supplies coming into this particular piece of machine. We would use the same method that I just outlined, trying to determine what the short circuit current rating is for a particular supply. It's important to remember that for each supply, we would have to identify what the short circuit current rating is for that supply, and then that would have to be provided on the nameplate, main nameplate. So you could have multiple short circuit current ratings on a nameplate for a piece of machinery. So with that, I'm going to turn the program back over to Joe for the last segment of this webinar, and he's going to talk about short circuit current rating versus arc flash, and certainly the hazards associated with arc flash and how you mitigate those using the short circuit current rating. Take it away, Joe.
Thanks, John. All right, so we basically talked about the machine SCCR, and the question that you have to ask is, do all of your machines and industrial control panels have an SCCR? And if they do, is it adequate for the available fault current? And if it is not adequate for the available fault current, do you have an arc flash label on there? And if you do, is there an electrical hazard? And basically, you're looking at, it's possible we have an electrical hazard because the SCCR is not adequate for the available fault current. And so we need to make sure that the SCCR is adequate for our arc flash label that we're going to be putting on our machines and our panels themselves. And so let's take a look at what the code talks about. The National Electrical Code basically says 110.16, arc flash warning labels, basically. In general, electrical equipment such as switchboards, switchgear, panel boards, industrial control panels, meter socket enclosures, and so on, shall be field or factory marked to warn qualified persons of potential electrical arc flash hazard. Right? That's the National Electrical Code. And then NFPA 70E basically states that we put an arc flash label on the panel on wearing what PPE that we need to wear and so on. All right? So let's look at what were adequate ratings that we're going to have. Now, we already talked about the SCCR itself. Do we have the adequate interrupting rating of the fuses and of the breakers, the overcurrent protection? So here we talk about 110.9, talks about interrupting ratings, making sure that we have adequate interrupting ratings, just like we have adequate SCCR for the panel. And so 110.9 interrupting rating basically states equipment intended to interrupt current at fault level shall have an interrupting rating at nominal voltage at least equal to the current that is available at the line terminals of the equipment. So basically, like John said, if we had 50,000 amps available, our fuse is rated for 300,000 amps, we're good to go. And if we're in the breaker, if we're on a 240 volt system, the 50,000 amps is adequate as well, or because this case, the breaker is rated for 65,000 amps at 240 volts. If we're at 480 volts, then we're at the 35,000 amps, and for a 50,000 amp fault, the breaker is not adequate, and we would have to change out the breaker and put in a higher rated breaker at the 480 volt level itself, right? So let's look at what PPE do I need to wear, okay? So we basically have already determined our short circuit current rating, and in this case here, we determined that our short circuit current rating for this panel is rated for 25 kA. The available fault current is rated for 15,000 amps, right? And we've calculated our arc flash. The incident energy level is 1.8 calories per centimeter squared, which would be a hazard category or a PPE level 1, which means that I would wear a 4-calorie shirt, 4-calorie pants, 4-calorie face shield, rubber gloves, leather protectors. And that would cover me for this panel, and everything is adequate. The other one I want to get into a little bit is what happens if we didn't calculate it, right? If we didn't calculate it, number one, we've got to make sure that the SCCR, number one, is adequate for the available fault current. And once we've determined the available fault current and making sure that the SCCR is adequate enough, then we can go and look towards the NFPA 70E chart. And so if I'm an OEM and I'm basically commissioning one of my machines in this building, has the arc flash calculation been completed? And in most cases, it has not. So what do you normally wear? Well, sometimes we don't wear anything going to the panel. We're commissioning it, making sure everything's working. Well, that's not exactly correct. We need to look at NFPA 70E, and NFPA 70E states at the bottom grouping, it says other 600 volt class, 277 volts through 600 volt nominal equipment. And normally we have 480 volt machines and 480 volt equipment. And so if I'm an OEM and I'm commissioning a machine or an industrial control panel, if it hasn't been calculated, I'm going to be having to wear a PPE of 2. And the PPE of 2 is 8-calorie shirt, 8-calorie pants, a balaclava, an 8-calorie face shield with rubber gloves, leather protectors, right? The other hiccup comes into play is the notes in NFPA 70, which means a maximum of 65 kA with a opening time. So the overcurrent protection device must open within 2 cycles or 0.03 seconds. a lot of times we don't know maybe what that would be on the opening time. But this is the chart that we would use if the arc flash hasn't been calculated and there hasn't been a sticker that shows me what PPE to wear. I wear a minimum then of a PPE 2, which again is the 8-calorie suit and so on. All right, so the question you got to ask yourself is, if my SCCR is adequate, so let's say my panel or machine has a 50 kA SCCR, and my available fault current is 40,000 amps. Then what label would I put on it? Well, after I have completed the arc flash calculation, I could put the sticker on the left, and I stick that on my machine where electricians and so on and OEMs know what to wear. Now reverse that. If I have my SCCR is 50,000 amps, and my available fault current, let's say, is 65,000 amps, now my SCCR is inadequate. And so now I really need to put the right label sticker on my panel until I fix the situation. Because if the electrician goes in there, it could blow up in his face, right? So we are in violation of the National Electrical Code when the SCCR is not adequate for the available fault current. So if the SCCR is adequate, I use the left label. If the SCCR is not adequate, I use the right label until I fix the SCCR and make it adequate for the available fault current. All right, so in summary, let's group all this together again. All right, so what did we learn today? All right, so let's look at basically safe and reliable operations of an industrial machinery is dependent upon the proper SCCR for the available fault current. And so we're talking about electrical hazards here and electrical safety. We want to make sure that the SCCR is adequate for the available fault current. And that basically is for operators as well as electricians getting into that panel, that qualified person going into the panel to troubleshoot. We want to make sure that he's properly protected, and then that the operator also is properly, doesn't have to worry about if a fault does come down the line, something happens to that panel, right? Number two, machine SCCR is based on the lowest SCCR of all industrial control panels associated with that machine. So like John said, if I have one feed going through the machine and then I have the robot controllers that are rated for 5 kA, right? If the main panel is rated for 65,000 amps, John's correct that I would take I would basically take 65,000 amps, do a fault calculation to those robot controllers, and if it drops, so for instance, if those robot controllers are 10 kA, using a number 10 gauge wire, truthfully, to go from 65,000 amps down to 5 kA, you only need about 30 feet of a number 10 gauge wire. And if they're 30 feet away, then basically my whole machine is rated for 65,000 amps because of the fault calculation I did on the robot controllers, even though the main was rated for 65 kA. And then we've got number 3, modify the SCCR or decrease the available fault current when SCCR is not adequate. So if we find out that we do not have adequate SCCR, how do we make it adequate? Well, we basically either drop the fault current by the transformers or conductors, or increase the SCCR by modifying the panel or using current limiting devices to basically increase the SCCR or reduce the fault current. And I usually say we're increasing the SCCR of the panel, not necessarily reducing the fault current. Current limited based on how you look at it, because you're kind of doing both things at the same time. And then finally, number 4, verify the SCCR is adequate for the available fault current when conducting an arc flash analysis. So we want to make sure when we're doing an arc flash analysis, we need to take into account the SCCR of the machines and of the industrial control panels and making sure it's adequate. I have seen so many machines that the SCCR may say 5 kA, especially like in air conditioning units. Air conditioning units are, greater than 60 amps. That's when the issue occurs, is that they're rated for 5 kA. And I see a PPE sticker on that air conditioning unit, and the available fault current's 20,000 amps or 25,000 amps. So we want to make sure that the SCCR is adequate for the available fault current itself, and to make sure we do it when we're doing the arc flash calculation. Right? So I'm going to, that basically ends our presentation, and I'm going to pass this over to Shannon, who will close out the presentation itself.
Thank you so much, Joe, and thank you, John. We have less than 5 minutes left, so I'm going to have time to ask just one question. When calculating SCCR for the machine, how do the requirements for NFPA 79 compare to UL 508A?
I'll take that, John. When we're determining the SCCR for the UL listed industrial machinery, all right, we must use the UL 508 supplement SB and use that method to determine the SCCR. NFPA 79 is the standard or guide to basically build the industrial machinery itself, how to build it, what kind of requirements you need. But UL 508A SB basically gives us the guide to determine the short circuit current rating itself.
Okay, thank you, Joe. We're not able to get to more questions from the audience. I apologize, but we will answer all of those questions, and we will send the responses, the questions and the responses out to everyone in an email following this webcast. Just a note, we have 3 more webcasts that are part of this series. You can register for any of those in the same portal where you accessed this live webcast. Our next one is on October 22nd, and it covers requirements for machine supply circuit and disconnecting means. This concludes today's webcast. On behalf of both UL and Bussmann, thank you so much for your time. Have a wonderful rest of your day.